Let's say you're Jacob Bernoulli in 1683. You're studying compound interest, which involves calculating interest based on the current value, not the initial value of something, as it is with simple interest. This makes the growth exponential. The formula for calculating compound interest looks something like this. P prime, the final amount in the bank, is equal to P, the initial amount in the bank, times this expression, where R is the annual interest rate, which is split over N, the number of times per year you compound, and T is the time in years which has passed. So say you put $100 in the bank, which gives 5% interest every year compounded biannually, so twice a year. After 3 years, you would have $115.97. And Bernoulli noticed that as the number of times you compounded per year n increased, the amount in the bank after time t increased. And this was obvious. But what he wondered was there a limit? And you might say that no, since when n grows larger, x to the n also grows larger. But think about it. As n increases, 1 plus r over n approaches 1. So this whole formula approaches 1 to the infinity. Does this equal 1? To solve this conundrum, we can consider a simpler problem. Let's say you have $1 in a bank, which offers 100% annual interest. You want to know how much money it'll have after 1 year. The only number which varies is n, the number of times you compound. And that gives you the following expression. At n equals 1, this equals $2. At n equals 2, this equals $2.25. And this growth starts to slow down because even if you compound daily, where n equals 365, this only equals $2.71. As n grows larger, if you want to get technical, the limit of this expression as n approaches positive infinity equals 2.7182 blah blah blah, also known as Euler's number, E. And the thing is, you can incorporate this number into the first formula we went over. Using some math more advanced than what I want to get into at this point, you could figure out that the limit as n approaches infinity of 1 plus r over n to the n equals e to the r, which you can then use to determine that if n equals infinity, p prime equals p e to the rt. And outside of this unlikely scenario, e has other uses in both calculus and probability. While I may cover these at some point, now is not the time.